Okay, good morning, class. Okay, sorry. Okay, so today we continue. Okay, for the next subtopic in chapter 4. Okay. Hi, good morning, Ayang. Okay. So good morning, Marian. Good morning, Yvonne. Okay. Good morning, Shonki. Alright. Okay, so today we're gonna finish for chapter 4, gas law. I think we still got two laws, right? Charles law and also Regius law, right? And then if you notice, I give you one link, right? So that link is for chapter 5. Okay. So I hope okay, after we finish chapter 4, you can click on that link and then you can use that link to learn for chapter 5, right? Okay. So I think we stop until here, right? Okay, so let's move on to the next topic. Okay, so here it said just now, sorry, last week, right? Last week we learned for Boyle's law. So we know that actually pressure is inversely proportional to the volume, right? And when the pressure increase, the volume will be decreased. Okay, and you already learned the formula P1 V1 equals to P2 V2. Okay, and we already know the graph of P against V is inversely proportional, while P against 1 over V is directly proportional. If PV against P, the graph is constant. Okay, so they learn how to calculate, okay, using the Boyle's law. Alright, so the next thing that we will learn is now today is about the Charles law. Okay, so actually Charles law is for volume and temperature. Okay, the relationship between the pressure of volume of gas and also the temperature. Right, so here, so let's say in the this is a diagram A and diagram B. So diagram A, it shows a gas molecule, right, in a cylinder, and according to kinetic theory, right, explain why the piston does not fall down. So even I put the load, okay, on the top of the pistons, okay, but the piston will not fall down. So why? Anyone want to try? Why doesn't fall down? Because the volume of the air molecule increase? No. So inside of it, there already has a gas molecule, right? So the gas molecule will collide with the wall of the container. So it will produce what? Yes, it will produce pressure. Okay, so because of the pressure, right, if you put the load on the top of the piston will not fall down because of the pressure. So inside of the cylinder also they already got the pressure, so that's why it will not fall down. Okay, and then for the diagram B, it shows the gas, right, in the cylinder is heated. Alright, so what happened to the temperature of the gas? What will happen to the temperature of the gas when you heat the cylinder? Yeah, so it will increase. Okay, so the temperature will increase, right? So this, what is the explanation here? So in a fixed mass of a gas at constant pressure, so the frequency of the collision between the gas molecule and the wall container is constant. So let's say if you don't add, alright, if you don't add any other molecule, okay, any air molecule inside of the cylinder, okay, so the frequency of the collision between of the gas molecule and the wall container is constant, means there is no change. Okay, then after that the gas is heated. So when the gas is heated, the temperature of gas also will be increased. So the molecule will move faster, okay, and this will make the kinetic energy also increase. So when the move faster, okay, when they move faster, the air molecule move faster. Of course, the rate of the collision, okay, between the air molecule, okay, and the wall container also increase. Okay, so there this will exert a large pressure on the wall of the container, right? And then the molecule will push the piston, okay, so that the gas expand, right? So the faster molecule now move in a larger space, and the pressure remains constant. Okay, so they collide with the walls more frequently. Okay, so the means the air molecule will collide with the wall more frequently because now it move faster, right? So after that, it will exert a large pressure on the wall. Okay, then it will push up the piston. So now after the volume is become increased. Okay, so that's why when the temperature increase, the volume also increase. Okay, it's just like when you ride a car, so you can see a tire. So after you take a long ride, right? So you can see the volume of the tire also increase. So this is why, this is because of the when the tire will produce the frictional force. So the frictional force will produce the heat. Okay, so means the air molecule inside of it will collide more uh, with the tire, with the wall of the tire. Then the pressure inside it will push. Okay, we push outward the tire, so the tire become bigger. The volume also increase. So that is the Charles law, right? So here you have to explain what happened to the kinetic energy of the gas molecule. Okay, so just now we already know when we heat the air molecule inside of the cylinder, the kinetic energy will increase. Okay, as the temperature increase. Okay, state a physical quantity that it must be kept constant. So this one, the answer should be pressure, right? And explain why the piston is pushed upward. Okay, because the volume of the gas increase, right? Because the pressure, large pressure, okay, inside of the container, it push, right? It push the wall container. Okay, it exert a large pressure to the container, so that's why the volume of the gas increase. So state the relationship between the volume of the gas and the temperature. So the volume directly proportional with the temperature. Okay, so this is the Charles law. Okay, how about the graph? Okay, so for the graph, okay, velocity against theta. Okay, so the theta or the temperature here. So the temperature, if it's in a degree Celsius, okay, the graph should be increasing linearly. Okay, so this is increasing linearly, right? But if you extend the graph, okay, if you extend the graph until it cut the x-axis, okay, so you will see it will cut at negative 273. So here what will happen at the negative 273? So this one we call it as the absolute temperature. Okay, absolute temperature. So here what will happen at the absolute temperature? So the first one, the kinetic energy. Okay, the kinetic energy of the air molecule, okay, is almost zero. Okay, so that means, right, the air molecule is not moving. Okay, it's not moving. So this one we call it as the absolute temperature, right? So remember, this one is only when the x-axis in degrees Celsius. Okay, so the absolute temperature, the kinetic energy of the air molecule almost zero. Okay, so almost zero, and the air molecule is not moving. So this one we call it as the absolute temperature. So negative 273. Okay, but how about if we change the x-axis, okay, to Kelvin, right? To Kelvin. So this is the graph for Kelvin, right? So you can see it's actually directly proportional. So there's a difference, okay, between the graph if the x-axis is degree Celsius or in Kelvin, right? So you have to make sure what is the x-axis here. So if the x-axis is degree Celsius, it should be this one is here, right? Actually, the line of the axis here. So this one should be increasing linearly, and for Kelvin is directly proportional. Okay. Okay, here what it says here at 0 degrees Celsius, the gas has certain volume. So here means at 0 degrees Celsius, okay, there is the gas still have a volume here, right? So when you keep decreasing the temperature here, okay, if you keep decreasing the temperature here, you will see at the negative 273, actually the volume of the gas is almost zero, right? So what is the absolute zero of the temperature? So this one is the lowest possible temperature, that is negative 273. Okay, this one is degree Celsius. So if you change to Kelvin, you add to add plus 273, right? So negative 273 plus 273, you will get 0 Kelvin. Okay, so the gas particle theoretically stop moving and have zero volume. Okay, at negative 273. Okay, and the temperature measured in Kelvin scale is called the absolute temperature. Okay, absolute temperature. So this one is actually how you want to change from degree Celsius to Kelvin. Okay, so this one degree Celsius. So let's say if you want to change to Kelvin, you just add 273. Okay, but let's say from Kelvin you want to change to degree Celsius, you minus 273, right? And then for the absolute zero, if in degree Celsius, right, so it should be negative 273 degrees Celsius. Okay, for Kelvin should be 0 Kelvin. All right, and the ice point, okay, you already know for the Celsius should be 0 degrees Celsius. Okay, for Kelvin is 273, because this one you change to Kelvin, you plus 273, right? So here you should get 273. And for the steam point is negative is 100 degrees Celsius. So if you change to Kelvin, you plus 273, it should be 373 Kelvin. Okay, so this is how you change from Celsius to Kelvin or Kelvin to Celsius. Okay, so Celsius to Kelvin plus 273, Kelvin to Celsius minus 273. Right, so this is the formula, right? Remember for the Charles law, and also the after that we learn about the Precious law, the temperature here must be in Kelvin. So let's say if the question give you the answer in degree Celsius, you have to change to Kelvin first before you use the formula, right? So here he asks you to state the Charles law. So we already know, okay, in the fixed pressure, okay, in the fixed mass of the mass of gas, in a fixed pressure, okay, the volume is directly proportional to the absolute temperature or to the temperature when its pressure is kept constant. Okay, so for a fixed mass of gas, the volume is directly proportional, okay, to its absolute temperature, okay, Kelvin, right, when its pressure is kept constant. So V is directly proportional to T. Okay, so that's for the Charles law. Okay, so this is the formula. V1 over T1 is equals to V2 over T2. Okay, so let's say if I take a tire. Okay, so this is before you take a long ride, and this one is after you take a long ride. So what is the volume before you take a long ride by your car, and this one is after you take a long ride by car. Okay, so this is the example how you want to use. So later we will do exercise on this one. Okay, so for Charles law, the pressure is constant. So remember the triangle. So this is actually P, right? So this one, when the pressure is constant, so you close P here. Okay, so should be V and T. So V divide by T. Okay, so that's how you use the triangle here. Pressure constant, you close the pressure. If the volume constant, you close the volume. If the T is constant, you close the T here. So should be left P and V. So that one is a Boyle's law, right? Okay, so this is the formula. Okay. So now I want you to try to change from degree Celsius to Kelvin, and after that from Kelvin to degree Celsius. Okay, so can you please try? If you already got the answer, you can just type in chat box, or you just can open your mic. Negative 98, 102, 727. Okay, so I check first for degree Celsius to Kelvin. So 320646 73 Kelvin. Okay, very good. Okay, and then for the Kelvin to degree Celsius, negative 98, 100, 727, and 102. Okay, very good. Right, so you already know how to change from degree Celsius to Kelvin and Kelvin to degree Celsius. Okay, how about this one? Okay, for this one, you already have to use the formula V1 over T1 is equals to V2 over T2. So remember, right, the temperature must be in Kelvin. Okay, the temperature must be in Kelvin, so make sure you change first. Okay, and you have to be careful. It said here the gas is heated until its temperature increases by 30 degrees Celsius. So means the final temperature is not 30. Okay, so you have to add with 27 to get the final temperature. Okay, so try to do this one and give me the answer. V1 divided by T1 is equals to V2 divided by T2. Isaac 220. Anyone? Maybe you got the different answer from Isaac. Okay, good. Isaac. Count first. Okay, so I got 220. Anyone got different answer? Okay, but for this one, they give you the answer wrong, right? This is wrong answer. Why? Because they didn't add the temperature here, right? Should be you have to add, right? Because this one is said it increased by 30 degrees Celsius. It's not like it increased until 30 degrees Celsius. Okay, so this will increase by 30 degrees Celsius. So this answer, this one is wrong answer. Should be 220 centimeter cube. Okay, very good. Okay, 220 centimeter cube. Anyone didn't get 220? Maybe you got different one. Okay, so I just give you the equation here. So this one is 200, okay, and this one should be 27 plus 273. You have to change to Kelvin. Okay, the temperature here, and then this one, the V2, you need to have you need to find. Okay, and this one is actually 57, all right, because it increased by 30 degrees Celsius. So it should be 57 plus 273. Okay, and then you just cross multiply it, right? So 200, this one is 300, and this is V2. I think this one got 330, right? So you just cross multiply like that, you will get 220 centimeter cube. Okay, so let's move on to the next question. So for this one, it said the diagram shows a glass tube containing some trapped air inside it. So at 70 degrees Celsius, the vertical column of trapped air is 29 centimeter. So what is the vertical column of the trapped air at the temperature of 57 degrees Celsius? So same, this one also, we assume this one is actually the trapped air is the volume here. Okay, so V1 over T1 is equals to V2 over T2. So remember, change first, okay, the degree Celsius to Kelvin before you put in the formula. You got 33 cm. Okay, so V1 is 29, right? Alright, and then after that it says when the 17 degrees Celsius, so should be 290 here. Okay, change to Kelvin. Okay, and this one is V2 also 330 here. Okay, so you just cross multiply. 29 times 330, you divide by 290, so you will get 33 centimeter cube. Okay, so make sure don't forget to put the unit, okay, for every calculation. Is it okay? Anything you want to ask, teacher? Anyone didn't understand how do we calculate for this question or the previous one, or you don't understand for the volume for the charge law? Okay, all right. So this is the answer, correct? Okay, so let's move on to the last part. That is a Pressure's law. So Pressure's law, sometimes they call it as a Gay-Lussac's law. Okay, so this is the Pressure's law is investigate between the pressure and the temperature. Okay, and of course there's a formula and we have to calculate. Okay, so just like just now, okay, that one is volume and temperature. So after this we will try to calculate, okay, the calculation problem for the pressure and the temperature. Alright, so this one is to determine the relationship between the pressure and the temperature. So it says here the diagram shows a gas molecule in the closed container. Okay, so this is the low temperature. So when the temperature higher, the molecule will move faster. So it will produce a greater pressure. Okay. So it asks you to explain what happened to the gas molecule when the gas is heated. So this one, of course, you already know the kinetic energy of the gas molecule will increase, and also same as the speed of the molecule also will become increased, right? So here the kinetic energy will be increased and it move faster and we collide more frequently. Right, this one we already learned. Okay, for B, it asks you to explain what happened to the gas pressure. So can you explain to me what will happen to the gas pressure since the kinetic energy of the molecule increase? So what will happen to the gas pressure? What will happen? So the gas pressure also will increase, right? So here the rate of collision between the gas molecule with the wall container increase. Okay, so when it move faster means it will collide more, right, with the wall of the container here. So when it collide more, what will happen? The rate of collision increase, right, and the gas pressure inside of the wall container increase. Okay. Then after that, you have to state the relationship between the gas pressure and the temperature if the volume of the gas is kept constant. Okay, so here when the temperature increase, the gas pressure also increase. Okay, so before I continue, right? So I already marked your paper 3 and I think I already turned into you. Okay, for the relationship, right? For the graph, some of you still using the higher like that, okay? The relationship like hypothesis. Okay, for the graph, you cannot use that one, okay? For the graph, the only things that allowed is directly proportional, increasing linearly, and also inversely proportional. So you have to see the graph. Okay, so don't use the higher, that one is actually for the hypothesis, or when you answer in paper 2. Yes, you can write like that. Okay, so please be careful. And also for the precaution, okay, I noticed, okay, mostly, like, I think like 90% of you got it wrong. Okay, because you don't use the word that I said make sure your eyes is perpendicular to the scale reading. I asked you to remember that sentence. Okay, so it's okay, we discussed that one on the Saturday, okay, Saturday class. Alright, so for this one, okay, this one you can say directly proportional. This one can, okay, but the graph cannot, right? So for this one, you can say the higher the gas pressure, the higher the temperature, the higher the gas pressure, right? So this one also, the temperature increase, gas pressure increase. Okay, so this one can. So it said here, so this one is actually the graph. Okay, for the graph is all this just same like the Charles law. Okay, and it's only the only thing they change is only the axis. Okay, just now V, right? So now because we investigate the P against T, all right, so just change the V to P, but the graph is same. Okay, so if you extrapolated the graph here, so if we found that the pressures become zero at the negative 273. So remember just now I already explained. So negative 273 is the absolute temperature, where the kinetic energy is almost zero. Why is zero? Because the volume is almost zero. Okay. So and then after that, the molecule is also almost cannot move at all. Okay. So this is the absolute temperature. Okay, when the temperature of the gas increase, the kinetic energy of molecule increase. So this one is actually to explain this part for the C part. Okay, and the molecule move faster and collide more frequently with the wall container, and it produce the gas. Okay, so that's really the pressure. So the pressure is increased. Okay, so this one is actually to explain for the C part. So state the Gay-Lussac's law. So this one is actually the pressure's law. So the pressure is directly proportional to the absolute temperature, okay, of a fixed mass of gas at constant value. Okay, so this is the triangle. So remember I told you this one we kept the volume, right, constant. So we close the V here, so it only left P and T. So this one is P over T. Okay, so the formula is P1 over T1 is equals to P2 over T2. Okay, so this is the formula. Right, and then this is the graph. Okay, so it just same like the Charles law graph. Okay, so just the axis is changed here. If the P against the theta is degree Celsius, okay, the graph should be increasing linearly. Okay, but if you extend the graph, it will cut at the negative 273, okay, at the x-axis. So remember, this is the absolute temperature, where the kinetic energy is almost zero, okay, and the molecule is not moving at all. Okay, but let's say if the graph is in Kelvin, okay, should be directly proportional. Okay, the graph should be directly proportional. Okay, so that's the two type of graph that you need to remember. You just need to see the axis here. Okay, just be careful with the axis. Okay, so this one I already explained. Right. So let's try to answer this question. Anything you want to ask for the pressures law? Anything if you don't understand? No. Okay, be careful with the unit here. Okay, this one they use 60 kilopascal. So teacher, should I change the kilo, okay, to the times 10 power of 3 or times 1000? Okay, so you have to see what is the unit for here. They say this one is kilopascal and this one is a kilopascal, so you don't need to change. But they say this one is kilopascal, this one is pascal, you need to change, right? And for the temperature, if they don't ask you to change, let's say they said, give the answer in degrees Celsius, then don't change. Let's say if the answer say, okay, change the answer to the degrees Celsius, then you change, okay? So for this one, you don't need to change to degrees Celsius. Just leave the answer in Kelvin. Okay, so just read the question carefully whether what's the unit the question want. Okay. So this one no need to change. So 60 kilopascal. Remember the temperature must be in Kelvin. Don't forget. For the gas law, the temperature must be in Kelvin. Okay, so make sure you change first. Okay, for pressure's law and also for the Charles law. For Boyle's law, no need because that one is pressure and volume, right? So you don't need to change anything for the temperature. So this one should be 293, right? And this one is 90. Okay, and this one is T2. Oops. 439.5. Right? 60 times T2, 90 times 293. So T2 is 439.5 Kelvin. Okay. Uh, yeah, 439. Okay. 439. Okay, correct. Okay, how about number two? P1 over T1 equals to P2 over T2. Make sure when you do a calculation question, put the formula. Sometimes there's a mark for formula. Okay, just put the formula. What formula did you use? And the second thing, make sure you put the unit, right? So this one is 300, I think. And P2 is you need to find. This one is 323, I think. Yeah. 387.6 kilopascal. Yeah, 387.6 kilopascal. Okay, correct. Just cross multiply, just same like this one. Okay, you multiply this one is multiply, right? Change, so this one should be divide. Okay, very good. Okay, let's check. Yeah, this one is actually they changed to degrees Celsius, so that's why you got 166.5. Okay, this one is 387.6. Okay. Okay, how about question number 3? So this one is actually 4 atm is the pressure. Okay. Yilin got 5. Z got 5. Kayi, Vireshva got 5. 5. Okay. So is it correct? I also got 5. Okay. So yes, the answer is 5 atmosphere. Okay, for this one, it says a motorcycle tire is found to possess a pressure of 3.2 atmosphere when it was tested in a garage at the temperature of 27 degrees Celsius. By assuming that the volume of the air tire is fixed, so this one V is constant. So V is constant means it involves P and T, right? So P1 over T1 is equals to P2 over T2. Okay. What is the temperature? 262.5 Kelvin. Yeah, 262.5 Kelvin. Any others answer? Maybe you got different one. Especially the quiet one, never want to try. I got 262.5 Kelvin too. Okay, very good. Okay, that one they changed to degree Celsius. Okay, so now we already finished for chapter 4. Right, so let's see the link. You already clicked the link I gave just now. So let's see how many students here. Only like 22 students. 24. Should be 35, right? So 9 more students. Okay, I will present. So maybe you can see how many of you still didn't. 29, 6 more. I cannot start the class if like not enough student. Then of course I can check which of you are not here in my class. Right? 3 more, 2 more. One more. Who is it? Yeah, okay, good. Alright, so we start the class. Okay. So you have to write your response. Okay, so far what you have learned. Okay. What do you think of physics? Okay, so easy or hard? Or maybe not so easy, not so hard. Okay, so wait, I see the response medium. At first I think physics, but now I stay in the middle. That will be much easier. Just one thing which is formula. I can memorize all the formula. Don't worry, they didn't put your name here. Okay. So maybe we can share. Okay. They didn't put your name, so you don't know who is it. Alright. So I just show you. Okay. What your friend, or maybe this is you actually. But there is a lot of formula. Hard, very hard. I have learned until but all the rest is sometimes I'm so worrying. Okay, some of you still typing. It's okay, easy, but I need to memorize the formula. Need many practice. Hard. Sometimes it's quite hard. Calculation, sometimes confusing, but chapter 3 very hard. Yes, I understand. That one is new chapter actually. Some chapter is easy, hard. Most of you said hard because of formula, right? Okay. Oh, some delete the response. You don't need to delete because I don't know who typed. It's okay. Gravitation. Yes, gravitation is quite hard. Confused, screaming, too many formula. Alright, don't worry because in exams sometimes they will give you a formula, okay? But not all lah. Some of the formula. We will see for this year SPM what formula they will give. Okay? So hopefully there's a lot of formula that you can use so you don't need to memorize. Okay? Alright, so thank you for your response. Okay. Very nice to see. Okay, but mostly say it's hard, right? It's hard. Okay, never mind. Okay, so I will continue. Okay, so the next part is, okay, so now you have to answer. Okay, actually if you see here, okay, you can see my presentation here, right? Okay, by the, at the Google Meet. Okay, if you see my presentation, I put the audio, and then you can see there is a like headphone here on the bottom here at the on your right side. Can you see the like the headphone there on the right side? Okay, so you can play that one. That one actually I attach a song for you. Okay, so not all slide lah. Okay, sometimes when I need your response, I put the sound there and audio there. Okay, you can play, right? Uh, so I hope you enjoy my 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 song that I choose. Okay. All right. So the next part is okay. So now you have to answer. Okay, you have to answer the question. So let's see how much do you know about wave. Okay, we do like a pre-test. Then after that, we finish about the wave 5.1. Then I give you the quiz, see whether you can answer after you learn or not. Right? So can you try to click the link? Is it okay? And also for this one also I give you the link. Can you click it? No? Invalid? Oh, wait. Then I give you another one. Wait for a moment. I give you admit. Maybe because I made a live quiz that one. So invalid. I try to use new thing because I just want to get your response. Before this only I'm the one talking, right? So let's try. I send you the link at the Google Meet, okay, at the chat box. Okay, so let's see you can answer or not. Yeah, I already sent in the. It's only like 20 question, I think. $17 more. 14. 12. 6 more. 5. 4. Should be like 1 minus 1. 35. 3 more. 2 more. Maybe you have a line problem. 1 more. All right, very good. Thank you. It's okay if you are wrong because we still didn't learn, right? But I noticed some of you got all correct. Ethan, Marian, KN, I'm not sure because you put the name here. BRCY. Isaac, you have a problem with your line? So I just give like 2 or 3 more minutes, okay, for you to answer. Okay, then we move on. Okay. Oh, Yvonne still got all correct. Okay, 10 kn already finished. So I give you 2 more minutes, okay, for you to finish the answer. Then I will end the quiz. Then we go to the chapter 5. Okay. And after this, I give you another test. Then you see whether there's an improvement, whether you can answer after this. Okay. Actually, what question you are wrong? What is the symbol? Okay. What is the part? Letter E. Okay. Some of you can answer. Solar flame. 5. Mm. Okay. Most of you already finished. Okay. So let's give your friends some time. Isaac, still all correct. Done? Okay, never mind. Okay, one more minute because I see some of you almost finished. After that, we end this quiz, right, and we continue on chapter 5. Okay, so it's okay for those who still did not finish. Okay, so later I will give you questions. Okay, so there's two more who still not finished, right? So after this, I will give you another quiz, right? After we have finished, then you can answer that one. That one I give you time until you finish. Okay. Right. So what I can see from here, mostly of you like 50%. Okay, you can understand. You can answer the questions. Okay. From the 20 questions, so 50%, like 10 questions, you got it correct. Okay, so let's see, right, whether there's an improvement after you learn for this chapter. Okay, so I will end here. Alright, so you already learn, okay, you already answer this quiz. So let's move on to next slide. Okay, so for this one, it said a stone, okay, a stone is dropped into the water. Okay, so what do you see? So let's see the video. Okay, for this one, you have to see at the mid there because at this app we cannot play the video. So I'm not sure why. Okay, so I will share my screen to you so we can see the video, right? Okay. So you can see the girl drop the stone into the water. So what can you see here when a stone is dropped into the water? So what can you see from the water? A wave, right? So if you like a wave, okay, that's spread outward, right? So it's spread outward. Okay. Okay, wave that move outward from the center. So that one is the water wave. Okay, so this is the example of wave. Okay, so the first one. Okay, so this is actually using a rope. This is using the slinky spring, and this is using the ripple tank. Okay, and this is by using the turner fork. Okay, turning fork. Okay, so this one all is produced by vibrating. Okay, so this one by using a rope is also a vibrating. Okay, and this one is the slinky spring also by vibrating. Okay, and this one of course for the ripple tank you have to vibrate. Okay, okay, you have to vibrate and then it will produce the water wave here. And this one is the turning fork, also is actually vibrating. Okay, so this is sound wave and this is the water wave. Okay, all right, so we move on to the slide that I gave just now. Okay, okay, So for this one, it says, okay, to study a vibration of deeper of a ripple tank. So this is called a ripple tank. Okay, so this one is actually to produce the water wave. Okay, so later we will learn about the phenomenon of wave. Okay, such as refraction, reflection. Okay, and also diffraction and also interference. Right. So there are four types of phenomenon in wave. Okay, for the water wave, okay, for the phenomenon for the water wave, we will use a ripple tank, okay, to see for all the four types of phenomenon, right? So here it said here, you attach a dipper until it's spherical and touch the surface of water. So remember just now, like in the video, okay, like in the video just now, wait for a moment, it's loading. No, no, not this one, this one. I'm sorry. Maybe cannot see because the line. Okay. All right. So here what will happen? So the dipper here will vibrate, okay, on the water, okay, and you will produce the spherical, okay, the water wave that in the spherical shape, okay. And what will happen, okay, it asks you to observe the surface of water when the motor does not vibrate. Okay, so what will happen here? Oh, cannot. Can you see the answer here? No. Okay. Now I know. Okay. I'm sorry, but I think we have to use a PowerPoint. Okay. Never mind that one. I will put in the quick. Let's say for the question we do the using the presentation. Okay. Sorry. This is my first time using it. Sorry, sorry. So let's see using the PowerPoint. Okay. Never mind. Okay, so for this one, it says you have to attach a dipper until it's spherical and touches the surface of water. So you have to observe the surface of water when when the motor does not vibrate. So when the motor does not vibrate, the water will be calm. Okay, so what happened when the motor vibrates? Okay, so it will be the water will move up and down. Okay, so let's see, I give you one video for the ripple tank. Okay, wait, I found the video first. Mm, no, where is it? Six. One moment. Okay, can you give me some time to find the video? Where is it? Oh, here. Okay. Ripple tank, ripple tank, ripple tank. Hmm. Wait, okay, okay. Wait, oh, wait. Okay, okay. So this is actually the ripple tank. So you put the white paper here, so you can see the shape of the wave here. Okay. So this is the they will put the light here. Okay, and the light will we go down here, and this one show you see which you will see the shape of wave here. Okay, and this is the deeper. So you see here, so this is the deeper. Okay, so the deeper will vibrate. Okay, so you see when the deeper is vibrating, right? Okay, so they will produce a wave here. So this is the circular wave, right? So this is the ripple tank. But our lab we didn't use this kind of ripple tank. Okay, we used the rectangle shape. So this one is a circle one, right? So this is circular wave. So you can see the wave spread out, right? Okay, so this is the ripple tank. So I just want to show you what does it mean when it says that when the motor does not vibrate, you can see there is no the water is very calm. Okay, but when it vibrate, the water will move up and down, right? And you produce and it will produce the wave like this. Okay, so you can see this is called as a ripple tank, right? Okay, so next move on. Okay, so it says here, let's say you have a turning fork. Okay, and you hold a turning fork. So when you hold the turning fork and the turning fork is not vibrate. Okay, so what will happen here? Okay, so there will be no sound. Okay, so remember the how to produce a sound wave. The sound wave is produced by vibration. So you see, very easy. So they say I'm talking just now, like talking now, right? Okay, I'm talking now and I hold my throat. Okay, you can see there's a vibrate. Or maybe when you talk, right? You can hold your throat so you can feel there's a vibration. So actually the sound is produced by vibration. Okay, so that's why sound need a medium to travel from one place to one another place, right? It means you need air, okay, because you need a molecule to vibrate, right? And then it send the sound energy to one molecule to one molecule until it come to your ears, okay, and your ears has an eardrum, right? So your eardrum also will be vibrate. Okay, so that one, the sound wave produced by vibration. Okay, so when you hold and then after you vibrate the turning fork, you can hear the sound. Okay, the turning sound, the turning fork will produce a sound. Okay, next part it says here a wave can be produced by an oscillating or vibrating system. Okay, so you can see, so it's produced by vibrating. Okay, so the oscillation of a dipper on the water surface produce water wave. Okay, the vibration of a turning fork in the air okay, produce sound wave. Okay, so this one produce a water wave. This turning fork will produce the sound wave. Okay, so it says here the water wave, okay, water wave carries an energy too. Okay, so observe the effect of energy carried by water wave. So this one is actually the tsunami. Okay, the tsunami. Okay, so what is wave actually? So you can see that the water wave also it carries energy, right? So it carries energy. So what does it mean by wave? Wave is actually a process of transferring energy. Okay, it's transferring energy from one location to another location, which is produced by oscillating of vibrating system. Okay, just now I told you, right? Like a sound wave. Okay, so the sound wave is actually they transfer the energy between the air molecule. Okay, what energy that they transfer? The sound energy. Okay, so the air molecule transfer the sound energy, okay, from one location to one location. But this one they use the air molecule, and of course they use a vibration. So the air molecule will vibrate, right? When it vibrates, it hits the another molecule, and it transfer the, while it hit the another molecule, it will transfer the sound energy too. Okay, and then after that, the molecule will start, another molecule will start vibrate, and then it hits another molecule, and then transfer the energy to that molecule, and the molecule will vibrate, so it will continuously, okay, until it reach to the location. So let's say in your ears, so it will reach your ears, and your drum also will vibrate, okay, it will produce the sound energy. Okay, so that is the wave. Okay, it's a process of transferring energy. So you have to remember it's transfer energy, not matter. Okay, so it's transfer the energy, okay, from one location to another, which is produced by oscillating of vibrating system. Okay, so let's see the video. So this one they produce the water wave. So let's see if you see at the side, okay, in front of the tank, okay. Okay, so you can see it vibrate from right to left, right? From right to left. So that is the direction of the propagation. Means which direction does the energy being transferred. So this one is from the right to left. Okay, so let's see right to, see it transfer from here to here. Okay, so let's say this is they say the leaf is produced is actually represent the what wave particle. So does the leaf move along with the wave here? Does the leaf move with the same as the time as the wave here is propagate from left to right? Does the leaf move too? No, right? So the leaf is not move. So what can we say here? So means the wave particle will not move, but only the energy being transferred. Okay, being transferred, not the particle, okay, of the wave. So that's why it stay at that time. Okay, so it just move up and down, but only the water is propagate from left to right. Okay, so that's the explanation. So what do you see on the water surface? So the water wave are produced. Okay, so what is the direction of the propagation? So the direction of the propagation is that which way does the wave travel? So this one we can see from the left to right, right? Sorry, from the right to left. Okay, And the leaf represent a water particle. So how does the water particle move? So it will move up and down only. Okay, it doesn't move along with the direction of the propagation of wave there. So it just stay there but only move up and down. Only the water transferred the energy. Okay, transferred the energy to another molecule. So far, are you clear about the wave? Anything you want to ask? Here, right? Okay, remember only the energy. You can see the water, the leaf does not move. It only move up and down, right? But it doesn't move along with the direction of the propagation of wave. So what we can see here, they only transfer energy. Okay, they only transfer energy. Okay, but the position of the wave particle is still same, right? So wave transfer energy. Okay, so that's why it's still at the initial position. Okay, only transfer energy but not transferring matter. Okay, so as the wave passes by, does the leaf move together? No, right? They only move up and down and it's still at its initial position. So this one means the wave transfer energy as they move along the water particle. However, the wave do not carry the water particle along with them. Okay, so that is why the leaf still remains about its initial position. Okay, so wave transfer energy without transferring matter. Okay, only the energy being transferred. Okay, how do wave transfer energy? Right? So when a stone drop into a pond, okay, so water wave are produced. So when you drop the stone, okay, so the water wave is produced, right? So the energy of the stone is converted to wave. Okay, so the energy of the stone is converted to wave. All right, and then the water wave will propagate on the surface of the water. The direction of the propagation of the water wave is from left to right. So it will move from here to here. So they say if you drop down the stone here, okay, the water wave will move from left to right. Okay, up and down. Okay, it move up and down. So where does the energy come from? It's actually come from the stone. Okay, the energy from the stone now is transferred to the wave, right? And then the wave will become like this. It will move up and down. Okay, from the left to the right, right? So the cork represent the water particle. So you can see the cork here only move up and down. Okay, and it will stay at this position. Okay, and the cord does not move together with the wave. Instead, it moves up and down about its initial position. So what is transferred by wave? So what is the transferred by wave? Anyone? What is the transferred by wave here? Yes, energy. So remember, okay, the first question that you asked, yeah, that the answer in the quiz just now, right? So they ask you what is being transferred, right, by the wave. So your answer should be energy. Okay, because I noticed some of you still answer energy and matter, right? So now I hope you are clear. It's actually energy that only being transferred. The matter is not transferred. We already see in the video. You can see the leaf will stay there. Okay, you only move up and down. Okay, even the wave you can see is propagate, right, from the left to the right. Okay, so that time only energy being transferred. Okay. Wave had transfer energy as they move along the water particle. However, the water does not carry the water particle along with them. Okay, so this one is actually by using a Sankey spring. Okay, so you have to put a ribbon, okay, you have tie a ribbon into the slinky spring, okay, and then you let the two peoples hold each end of the slinky spring. Okay, so move NA. So for this one NB, so this one the hand will not move. Okay, we just stay there. Okay, we'll hold that. It's fixed. Okay, only the NA is moved. Okay, so you can see it says here move the NA of the slinking spring from side to side while NB is fixed. So means from here to here. It will move, okay, like this. Okay. And it says here, have you observed the movement of the wave, okay, along the slinky spring and the movement of the ribbon. So you can see it move up and down, but the ribbon will still here. We stay here, right? It will not move together, right? Until the end B here, until B. They only stay here, but the slinky spring will move up and down. So that's another way to investigate the propagation of water or as a transfer energy. Okay. So here is question. What is it felt by the people at NB after the slinky spring is moved from side to side? So what will happen? What will the at the what will the people that the what the people at the NB will feel? Okay, when the slinky spring is moved from side to side. What they will feel? Anyone? Yes, very good. Vibration, right? Remember the wave transfer energy by using a vibration of the oscillation system. Okay, very good, Ziying. Okay, very good, Virish. Wow. Okay, very good. You will feel the vibration. So, what is the direction of the energy transfer? Okay, so from this one is from left to right. Okay, from left to right. Since it's vibrate from here, so the energy will be transferred from left to right. Okay, and describe the movement of the ribbon tied to the slinky spring. So it will be stay in the fixed position, but it move up and down. Okay, it will move up and down, but it will stay at the same position. Only move up and down. Okay, so here the movement of the wave from NA to NB, it transferred energy. Okay, so the right ribbon does not move in the direction in which the energy is transferred by wave. So only energy being transferred, the ribbon will not move. Okay, so what is the conclusion? The wave is produced, okay, when a medium vibrates at the fixed position. So you can produce a wave, okay. So if you vibrates, okay, a medium in a fixed position. Okay, so the propagation of the wave and transfer energy from one place to another without transferring the matter of the medium. Okay, so this one we already know. Okay, so let's see this video. Okay, sun is a form of wave. What happened to the flame? Okay, what will happen to the flame? Yeah, the flame also vibrate. Why? Because they transfer energy, the air molecule, right? There's an air molecule between the flame and also this cup, okay? And then it will vibrate the flame here. Right? So the air molecule transfer the energy, okay? Okay, so it says here sound is a form of energy. What happened to the flame when the hand beat the drum? Why? So the flame reflect. Okay, sound waves transfer energy from the vibrating drum to the candle flame. Okay, causing the flame to flicker. Okay, so the sound wave is transfer the energy. Okay, from the vibrating drum to the candle flame, causing the flame to flicker. So what medium that they use here is actually the air molecule. Okay, so the air molecule will vibrate and it transfer the sound energy. Okay, and it cause the flames to flicker. So as the wave passes through the air, do the air particle move along with the water? With the wave? No, the air particles vibrates about their initial position. Okay, they only vibrate. Then after that, it hit another molecule. Okay, then another molecule hit. Okay, but they will stay at the same position. Okay, they just collide with another molecule. So of course, after there's a molecule, right, beside each other, so we just vibrate, then it will collide with another molecule and it send energy there, then but it will stay at the same position. Okay, just to transfer the energy. Okay, so the air particle transfer energy to the next particle but stays about its initial position. Right, so you already see the video just now. So as the wave passes through the air, the energy is transferred without the transferring of matter. So the air particle stays there, but when it vibrate, it will collide with another particles, then it transfer the energy. Then it move to another, it will collide with another particle, then it transfer energy. But that will be still same at the same position, right? So here activity 2, okay, to investigate the propagation of wave as transfer energy. So a candle is put in front of the speaker. This one is the same they put the drum just now. Okay, so observe the flame when the speaker produce sound. Okay, state the direction of the movement of the flame. Okay, so can you state the direction of the movement of the flame? Left to right, left to right. Okay. So yes, okay, we'll move left to right or the flame is flicker. Okay, so how does the flame receive energy to move? So this one is actually by the vibration of the speaker, okay, and it's transfer the energy of sounds to the flame. Okay, so the sound will transfer energy from the speaker to the candle flame, right? So the air molecule will vibrate. Alright, so when energy is transferred by a waveform vibrating sources to a distant receiver, there is no transfer of matter between the 2 points. So there will be no energy will be transferred. Okay? Sorry, there will be no matter being transferred, only energy being transferred. Okay, so that's the video. Okay. All right. So energy transfer through sea wave motion can be huge. Okay, for example, during tsunami. Okay, so the energy carried by water wave from the sea can cause great damage to the surrounding. So most of the energy come from the winds blowing across the surface of the sea. Okay, so that's why you can see after the tsunami, okay, many buildings, right, can be destroyed only by the tsunami because the wave energy it can carry a high energy, right? So this is the tsunami effect. Okay, you can see this is before, then this is after the tsunami. Okay, so I think I will stop until here. Right, so I'm sorry, okay, for the technical problem. I don't know what happened. Okay, so never mind. Now I know. So after this, maybe for the question we can use that presentation, but for notes, okay, for theory I will teach using the PowerPoint. Okay, is it okay? Any question you want to ask? Okay. All right. So I see you on Thursday. Sorry. Yeah, I think on Thursday, right? Okay, on Thursday we will continue on this one. Okay. So if anything, you can text me. Right. So stay safe. Take care, class. Okay. Goodbye. Thank you. Bye.